Thank you, Alex, for the introduction. Yeah, I'd like to thank the organizers. It's been a really great conference so far. Yeah, as Alex kind of alluded to, there's a lot of words in this title that might not make much sense at the moment, but hopefully by the end of the talk, they will do. And these are the main references for this. So it's really actually two effects, but very strongly related, that I'll talk about today. And this first one is both theory and experiment, and the second one is a pure theory paper. But let me just give you a flavor of these non-reciprocal transport effects, which have become quite popular recently. And as you learn, maybe not in kindergarten, but at least at school, that Ohm's law tells us that the voltage drop across a sample or a device is proportional to the current, and we call that constant of proportionality the resistance. And essentially, this is just linear response theory. And so what I'm talking about today is actually kind of the grown-up version of that, but it's a Friday morning, and you know, we're still young researchers, so it's not going to be too much more complicated. So I'm just going to think about the next term that's allowed, which is an I² term. And as you can see, that term is actually very interesting. And you can see from this effect, you can see that from the way that I've written this, with this gamma, we're taking out a factor of magnetic field. And what such an I² term actually tells you is that your resistance due to a current flowing in one direction compared to the resistance of a current flowing in the other direction must be different. So already you can see that that must mean that inversion symmetry has to be broken to have such an effect. And if this is coming from the band structure of material, of course I can have PN junctions and this would already give me such an effect. But if this is a band structure effect, then I also have to break time reversal symmetry. And so I should already say from the start that everything that I'm going to talk about today is not a magnet. It's external magnetic fields applied. But for most of you who are interested in magnetism, already you have broken time reversal symmetry. So a lot of the effects that I will talk about today should also occur in magnets. But here I'm going to have an external magnetic field. OK, so just a quick outline. First, I'm going to introduce topological insulator nanowires, which probably most of you haven't heard about. I know Alex has heard about them probably far too much now. And then I'm going to talk about this magnetochiral anisotropy rectification of the normal state. And then finally, this superconducting diode effect, also in the topological insulator nanowires. This is an effect which has become kind of a hot topic at the moment. It seems like on arXiv, every week there's a couple of papers on it. But first, starting with the topological insulator nanowires, and this is a much broader project than just this paper, and hopefully it will become clear why. But most of you know what a topological insulator is, and in particular, I'm talking about 3D topological insulators. And if the most common setup is that I just have a flat surface, and on that surface, my Hamiltonian is the same as the Dirac equation, and in the case of a 3D topological insulator, those surface states obey a 2D-like Dirac equation. And one of the most prominent examples of that is something like bismuth selenide. But what I'm interested in is actually when you make this into a nanowire. So you make a thin wire of topological insulator. And then what happens is that these surface states become quantum confined around the cross-section, as you can see from this plot here. So this is a plot of a tight binding model of just a square nanowire. But this works for any geometry. And the wave function wraps around the edge of the nanowire. And for the momentum parallel to the nanowire, I get quantized, or I get subbands, where each of these subbands has a different angular momentum for the state going around the nanowire. And that angular momentum actually is a half integer. The reason for that is that in the topological insulator, as I go around the cross-section of the nanowire, my spin is rotating. And so it rotates by 360 degrees. And of course, if I rotate a spin by 360 degrees, that gives me a minus sign. So the spatial part also has to come with a minus sign to have overall periodic boundary conditions. And so that's why I get these half-integer angular momentum subbands. And we had a previous, it was the last work of my PhD, with the Cologne guys, where we've had a topological insulator nanowire. This is how they look. Well, not really. They're a bit more messy than this. And as a function of gate voltage, they measured these periodic peaks and dips, and averaging over a lot of sweeps, because these systems are very complicated. There's a lot of charge disorder and many other things going on. But once you average over them, you start to see quite clear, so that this is this solid line. You see a lot of peaks in the resistance. And this is coming from exactly the bottom of these subbands, where I get a Van Hove singularity. And so therefore, I get an increase in the scattering rate, and so an increase in the resistance. And I should say here that there have been previous, a lot of, or quite a bit of work on previous topological insulator nanowires. But here now, this is really a bulk insulating wire. And so you see the Dirac point, and the bulk is kind of, the bulk bands are far away. So why would we be interested in that? And one reason, or the main reason that I'm interested in it, is that at the end of the day, you can get Majoranas from this. And one way of doing that is, we showed in this paper here, is that actually by gating the nanowire, I split my subbands. And particularly if the gating is large, then what happens is that I start with the dashed line. It's a doubly degenerate subband with plus and minus this angular momentum. But then when I apply the gate, my angular momentum is no longer a good quantum number. And so I split the subband and get these spin split bands with a finite spin polarization. And actually, this comes from the fact that I localize my state more to the top of the nanowire or more to the bottom. But actually, you'll see at k equals 0, because of Klein tunneling effects, the fact that I have a non-uniform potential actually has no impact. And that's a fundamental thing of the fact that the TI surface state is described by a Dirac equation. And what's nice about this is that compared to these other nanowires, which have become very popular, well, maybe not so popular anymore, for Majoranas, is that the energy scales, for my mind, are much more reasonable. So we're talking about many MeV, for example, of the effective spin-orbit coupling from the fact that so the size of this band splitting. I think one of the nicest things about these TI nanowires is that they can actually use orbital effects, so I don't need to rely on the Zeeman effect to open the band gap at k equals 0. For example, this spin orbit length is also very short. So for Majoranas, all of these energy scales are, for me, in a much more reasonable energy range, because I like my energy scales in MeV and not micro-EV. So the basic proposal is not too dissimilar to the normal one for Majorana bound states, though. So by applying a magnetic field parallel to the nanowire, mostly due to orbital effects, I can open a helical gap. And if I then have the superconductor on top, what that means is that the interior gap closes and then reopens with the opposite sign. And that means that I have Majorana bound states, and these are well localized for a very large energy scale of several MeV, which is kind of order of magnitude or more than compared to the normal semiconductor nanowires. So that's why I'm interested in it. And one of the reason that, or the main thing that motivated now looking at these non-reciprocal transport effects is kind of coming up and showing that actually the ingredients that you expect for this proposal to get Majorana bound states are actually there in the nanowires to start with. So that was the motivation now about looking into this magnetochiral anisotropy rectification, which is this normal state rectification of current flowing in one direction being, or the resistance due to current flowing in one direction being different than the resistance flowing in the other direction. Yeah, sure. Yeah, so this is only sorry, I should have been clear about it. So this is only a single subband, and then, but let me go back here. This is a single subband, and so the full system, you have multiple subbands and all of them split. Yeah. So yeah, this is a single one, and there's actually, they all have different angular momentum, and they all have then different splittings. Why is this? Okay, so the motivation then for this magnetochiral anisotropy is actually, I think from the theory perspective, extremely simple, is that rather than applying the magnetic field parallel to the nanowire, as you would want to do to get any kind of Majorana's, by applying the magnetic field parallel to now the spin polarization, which arises due to this band splitting, then I shift my bands relative to each other, because of that, this is where this magnetochiral word comes from. I have a difference in the band structure. So I've kind of taught my band structure that actually inversion symmetry was broken. Because of Kramer's theorem at zero magnetic field, then although I had broken inversion symmetry, at that point my band structure didn't know I needed to apply this magnetic field. And from the theory perspective, I'm not going to go into the full details, but it's a relatively simple calculation, actually, that using the Boltzmann equation, you can calculate this, the contribution to the current, which is second order in electric field. And the result is, in 1D is actually very simple and I think quite intuitive, that it's just this band curvature. So rather than being the actual, so for the first order conductivity, it would be the difference in the velocities. Here it's now just the difference in the band curvature, which means the second derivative of my subband spectrum. And because of the fact that I've broken time reversal symmetry, this quantity then becomes finite. And so the theory prediction, just using this simple Boltzmann equation approach, was that I should get a peak. So as I tune my chemical potential by also applying a small gate voltage, then I should get a peak close to the bottom of one of these subbands. And then as I further tune it, when I hit this second subband, so that these are the different colors here, I get another contribution which starts to cancel the contribution from the first subband. And at some point then actually I get a change of sign of this gamma, this rectification coefficient that comes into my modified Ohm's law. And that would then be a signature of the fact that I have this large band splitting, which is required now to get these Majorana bound states. But I should say here, at the moment, there's no superconductor. That'll be the second part of the talk. How long do I have, actually, Alex? OK, so then I should speed up. OK, so it actually turned out that already Yoriciando in Cologne, they had the perfect system to measure this. We were actually looking into this for different reasons. But it was a nanowire etched from an MBE film. And essentially, all you need to know, it's a bulk insulating nanowire. And as a function of gate voltage, you see that there's an increase in the resistance. And you see these little peaks and dips that occur here, which are not as clear as in the previous data that I showed. But the expectation is that these are coming from these quantum confinement features. So the fact that I have the subbands and therefore Van Hove singularity is increasing the resistance. Let me also say that to really convince you that this is quantum confined surface states, if you do apply the magnetic field parallel to the nanowire, you see Aharonov-Bohm-like oscillations, which are set by now the cross-section of the nanowire. And so this is because of the fact that by threading a flux through this state which wraps around the surface of the nanowire, then I get this AB-like features in my resistance. But what we're interested in is the second harmonic. And so to really measure this, so to measure these non-reciprocal effects, because it's proportional to I squared, what you can do is put in a low frequency AC pulse, or not pulse, but a low frequency AC current, and then measure actually the second harmonic of that, and that filters out for this I squared term. And so zooming in now on a gate voltage range where you see these regular peaks and dips, which should come from the subband features, already you can see that there was a finite second harmonic resistance, which is antisymmetric in magnetic field. So you can get trivial second harmonics quite easily. So you've got to be very careful sometimes with these measurements. But you have an antisymmetric component of the second harmonic in magnetic field. It grows linearly, so the resistance grows linearly with current, and also it has the expected just boring cosine dependence of of the size of the effect as you rotate now the magnetic field, for example, in the plane which is perpendicular to the nanowire, but also if you do it in the plane where you go parallel to the nanowire, you also just find a cosine with the maximum in a direction which is perpendicular to the nanowire, which is what you expect for the spin polarization of these spin split subbands. What was cool is for many reasons, partially because of the fact that it's a 1D system, partially because of the fact, I don't know why there's a times there now. Okay. But it's partially because of the fact it's a 1D system, also because of this very nonlinear band structure in the TI nanowires. It was a very large effect. For this gamma rectification coefficient was, as far as I'm aware, the largest that's been reported. Okay, so the theory prediction, though, was that in a single subband, I should get this change of sign of my gamma, of my rectification coefficient. And indeed, so if you now zoom in further and look at just a single set of these dips and peaks in the nanowire, then as a function of gate voltage, you see a change of sign. And this here is now just mapping out that change of sign for different gate voltage values as a function of magnetic field. And at some points, of course, things get a bit complicated. So, for example, here you see that it's not so clear what the sign of this gamma is, but you very clearly see that it goes from one direction as a function of this outer plane magnetic field to another direction, and then back to the original direction. So you see this oscillation already from these maps of the B sweeps of the second harmonic. And so that shows that this because of the fact this effect can only happen if you have broken inversion symmetry, it showed that this large band splitting is present in these nanowires. And that's required for the Majoranas. I don't know why this is. Okay, I should probably speed up now. This is weird because it's my own presenter and I don't know why. There must be some interference effect. Okay, so let me quickly now talk about the superconducting diode effect, which is actually kind of a superconducting equivalent to the magnetochiral anisotropy. So if I have magnetochiral anisotropy of the energy spectrum, then I can also have this superconducting diode effect. And you might think, well, if it's a superconductor, how can I have a difference in resistance? But it's actually a difference in the critical current, which is the manifestation of this of the fact that I have this inversion symmetry broken in the system. So what that means is that if I have inversion symmetry broken and I have a broken time reversal symmetry, then my critical current in one direction of, for example, a nanowire, is different than the critical current in the other direction. And the reason that gets called the diode effect then is, of course, if I have the critical current is slightly higher in one direction than the other, then in one direction I have a supercurrent flowing, and in the other direction it's just normal diffusive transport. I think the most exotic setup that I've seen of this is in twisted bilayer graphene, where they make a Josephson junction, and when they tune this into the regime where they expect to have the material in the middle of the junction is magnetic, they really see you can, I don't know, it might be a bit small here, that there's an anisotropy in the critical current depending on the direction of the magnetic field which is applied. So you can see here that where this red curve is for the magnetic field in one direction, and then for the magnetic field in the opposite direction, you get the blue curve, and you can clearly see that the critical currents are different between plus and minus magnetic field. But we're not talking about anything quite as exotic as that. I'm just now thinking about these nanowires, which we would like to use for Majoranas, for putting the superconductor actually into the system now, rather than the normal state transport I discussed before. So quickly, I probably don't have time to go through the full theory, but the basic idea is that I can model the supercurrent in the system by thinking about a finite pairing potential. So a finite momentum pairing in my in the nanowire with the proximity-induced superconductivity. And what the momentum then, or this finite momentum tells me is that at some point my system goes completely normal as a function of this momentum q, and at that point I can associate that with the critical current of the system. And when I have this magnetochiral anisotropy, what you find is that the critical current for positive q and negative q are different. And there's a very simple formula for this. And so the idea is that, again, if I have broken inversion symmetry and I also then break time reversal symmetry, in my case by applying a magnetic field, then I can get some measure of how much inversion symmetry is broken in the system. And just for the theory tells you that there should be a maximum in this effect close to the point at which this band crossing occurs, which is actually where you would like to be to get the Majoranas. And what's actually cool is that, so this is when I have just the magnetic field as in the previous case. So these plots now are just the magnetic field as in the previous case, perpendicular to the nanowire. But when I also have a component of the magnetic field parallel to the nanowire, then I get a modification of the diode effect only in the region where I'm opening this helical gap. So I can use actually this diode effect to kind of diagnose that I'm in the region of parameter space that I would like to be in to get Majoranas. And it's a kind of completely separate way of checking that actually I'm really opening this helical gap and I'm changing the interior gap of my hybrid superconductor TI nanowire system. I should also say actually that in this paper, I focus here on the TI nanowires, but you could also do this with Rashba nanowires, and it all works almost identically. So why might you be interested in that? Well, one big problem in these nanowire systems is actually knowing how big your spin-orbit coupling is in, for example, the Rashba case. So that Daniel and Yelena, in a previous postdoc of theirs, have a paper where they show, I think, probably one of the biggest problems in these Rashba, well, they have many problems in these Rashba nanowires, but one of the biggest problems is that once I attach the superconductor, then I renormalize and modify all of the parameters compared to the case where I'm just looking at the normal state. And so I get a reduction, for example, in the spin-orbit energy as a function of the coupling between the superconductor and the nanowire, which means that if I want to have a large induced superconducting gap, then actually my spin-orbit coupling is vastly reduced. And to be honest, no one really knows how big the spin-orbit coupling still is in the residual spin-orbit coupling once you put your superconductor on top of the Rashba nanowire. We had a paper recently where we showed that for the TI nanowires, actually this is not such an issue, but it's still there, these metallization effects. But still, there's very little evidence of the size of the inversion symmetry breaking, so in other words, the size of the spin-orbit coupling in either TI nanowires or Rashba nanowires. So by measuring this superconducting diode effect, you can get some kind of idea of how big the inversion symmetry breaking is. Okay, so that's how it works. So let me just quickly say the people that were, or the main people, that there's many more that I haven't shown here. But from the Basel side, the main people are Daniel and Yelena. This is our group photo. I mean, group retreats in Switzerland are really nice. I think Alex is just somewhere here. And then from the Cologne side, the first stories I told you about with these VLS nanowires was mostly Felix and Oliver. And the magnetochiral anisotropy measurements were done by Matthias, and all of this is within the group of Yoichi. And a lot of this work was started with my PhD supervisor, Achim Roche, who's also in Cologne. Okay, so let me just quickly summarize. And the main thing I want you to take home is that you can you can tell a lot about symmetries in a system by measuring these non-reciprocal transport effects. And for me, in the recent years, the one thing that's been cool about this is that we've been able to show that these, in TI nanowires, you have this spin split band structure, which is required for the Majorana bound states. And another nice thing about these non-reciprocal transport effects is this superconducting diode effect, which can also tell you about symmetries, but when now I put the superconductor on top. And that's important because if you want to have anything like a Majorana, you need to have something like spin-orbit coupling, and there's not many ways to actually measure that. So I think the superconducting diode effect is also a really cool effect, but mostly because it tells you a lot about the symmetries of your system.